Hello friends, you have seen in the last video that how to calculate the maximum moment in a cantilever sheet pile and the pressure distribution and the depth of embedment. Now we would like to see uh, if there is going to be a cantilever sheet pile embedded into the ground having the ground properties known to you. Let's say in the last video you have seen that there is a water table. There is the water table, and this is the cantilever sheet pile. So there is the cantilever sheet pile. You have seen that the pressure distribution, you have seen depending upon what is the unit weight above the water table, what is the submerged unit weight or the saturated unit weight below the groundwater table. You have seen the pressure distribution. This pressure distribution you have seen and you are in a position to find out the lateral pressure. This is going to be the active pressure, which we had taken as P1 prime. This hole is going to be P2 prime. And the pressure distribution is going to change like this. And it extends like this. And then it is going like this. Is going like this. And the whole calculation is going to be quite rigorous. So we would like to see the simplified approach. The simplified approach is going to be little approximate in nature, but it will give you the idea that how to calculate the depth of embedment D. So in simplified approach, the objective is to compute depth of embedment, which is capital D as shown in this figure. So there is quite rigorous in nature. You need to find out this value Y. I have already explained all those things. This is going to be Z and all those things. The pressure here is going to be PPB1, PPB2, and here at this point this pressure is PP at E, or you call it, if this point is called O, then it is called PP at O. So this approach is quite rigorous. In nature. So a simplified approach for this cantilever sheet pile, let's say this is the cantilever sheet pile, and if you want to draw the pressure distribution diagram, this becomes the total height of the cantilever sheet pile. So, and the depth of embedment is called capital D. Now, in this approach, what we do it, that we assume that this active earth pressure gets developed when the sheet pile is going to rotate under this, like this, about some point O, then the active earth pressure is going to develop here. So this is going to be the total active earth pressure distribution, and this active earth pressure distribution is going to be at H plus D if the ground properties, if you know the value of unit weight, gamma, if you know the angle of internal friction, therefore you can calculate Ka. So the active pressure is going to develop on the backfill side, that is on the right hand side of the sheet pile. And naturally, at any depth Z, this pressure will be given by K times gamma Z. So the active pressure PA at any depth Z will be K times gamma Z. And therefore, at H plus D, this pressure will be equal to K into gamma into H plus D. And this will be acting, if you find out the area of this pressure distribution diagram, then this total thrust, active thrust PA, will be acting at a distance of H plus D divided by 3 from the base. So the top point is called A, and the base point or bottommost point is called B. And therefore, from the bottommost point, the point of application of the active thrust will be at H plus D by 3. So it is assumed that this side, it is going to be completely active on the right hand side of the sheet pile. And this PPB1, that is the passive pressure which is getting developed over here, is going to be here one resistance R, which is equal to PPB1. And on this side, if it is going to be, it is assumed that this is going to be completely passive. So here, if it is going to be passive in nature, passive pressure on the, so it is going to rotate like this, and therefore it is going to compress the backfill on the left hand side, that is below the depth of embedment. So there, below the dredge line, if the dredge line, let's say, call it as D, so this, in this zone, or the dredge line, you may call it by some point, not D, D is the depth of embedment, AB, let's say this is called C. Then here, from C to B, it is going to be passive earth pressure. And this becomes the resultant of passive thrust. So area of the pressure distribution diagram, and this will be at the bottom, this pressure is taken as Kp into gamma, the unit weight, into D. So this is called the simplified approach. And this approach will give you the depth of embedment. It is quite simple. And therefore, by taking moment about so in simplified approach, we can easily find out the depth of embedment by taking the algebraic sum of the moment about the bottom point B and equating it to 0. You will be getting, due to the thrust, PA multiplied by H plus D by 3 must be equal to this PP, that is the passive thrust, that is PP into D by 3. So you can find out the moment sigma m about B. So about this point, find out the moment. Or you can say that PA is simply half into base, that is K gamma into H plus D into H plus D, that is H plus D whole square. That is the value of PA. And therefore, this value is can be written as where PA equal to this, and this PP will be half into base, that is Kp gamma D, Kp gamma D into this height, that is D. So it becomes D square. So if I am going to substitute here in this, so PA will be given by half K gamma H plus D cube divided by 3. And if you take it this side, minus half Kp gamma D square into D, that is, it is going to be D cube divided by 3. So this equal to 0. So the simple equation here is going to be K gamma H plus D whole cube minus Kp gamma D cube equal to 0. So from this, K is known because phi value is known, and therefore K is always known to you. Gamma value is the ground properties, backfill properties, and below the dredge line, gamma will be known to you. Height of the cantilever sheet pile is known to you. You need to find out the depth of embedment. Kp is known to you. Gamma is known here, and depth of embedment we want to find it out. So you get a equation, cubical equation, and therefore that equation, if you solve it, so solving one, we get the value of D. Once you get the depth of embedment, increase it increase D by 20 to 40%, and therefore you can calculate the D provided equal to 1.2 to 1.4 times calculated D. So this is how the simplified approach can be used. Though it is approximate in nature, but it is a very quick technique, and you are in a position to calculate the depth of embedment in no time. So this simplistic approach is very popular, and it gives you fair idea about how to compute the depth of embedment. Now, let's say the situation at the site is like this. You can see one example on this. So one example, if you take it, let's take one example. In the previous problem, cantilever sheet pi, you have seen that you have a cantilever sheet pi. This cantilever sheet pi, the dredge line, and there you had the water table also, and this water table was at a depth of 2 meters. So H1 equal to 2 meters, and from here up to the dredge line, H2 was 3 meters in the previous problem. So similar example, you can take it, and this is the water table. The gamma above the water table we had taken as 18 kilonewton per meter cube, no change, and phi is going to be 30 degree. And below the groundwater table, gamma prime we had taken it as 10.19 kilonewton per cubic meter, and phi prime equal to 30 degree. And here also it's a granular backfill, and here also you had below the depth of embedment, you had the value of gamma prime equal to 10.19 kilonewton per cubic meter, and phi prime equal to 30 degree. So using, in this example, using simplified approach, you need to calculate depth of embedment. How will you do it? Just now draw the pressure distribution diagram. First of all, for given value of phi, let us calculate K and Kp. This is going to be 1 minus sine phi upon 1 plus sine phi. And for phi 30 degree, this is going to be 1 by 3. And Kp is 1 upon K. So this is going to. So the solution begins like this. And then you need to draw the pressure distribution diagram as we have just now seen. So here above the water table, it is going to be active, So at H1 equal to 2 meter, the value P1 prime, you should calculate it, and that is going to be K times gamma into H1. And if you substitute, this is going to be 1 by 3 into 18 into 2. So this is going to be 12 kilopascal. So from 0, because at Z equal to 0, it is going to be this one. So this is going to be 12 kilopascal. Now, at H2, so the now situation is changing. Here, it's a water table, and therefore, this is going to be 12 kilopascal. Now, below 2 meters, so from 2 meter onwards, 2 meter to 5 meter. At this point, let's say this is A, this is B, this point is C, this point is small d. So at D, from to 5 meter, the pressure distribution can be calculated, and at D, the pressure will be P1 prime, so P2 prime will be P1 prime 12 plus. It is now going to be K into gamma prime into H2. So therefore, it is going to be 12 plus 1 by 3 into 10.19 multiplied by 3. So you can calculate it. This becomes 22.19 kilopascal. So from here, this pressure is here up to here. This is going to be 10.19, and total it is going to be 22.19 kilopascal. And below this, because it is going to be active. Now, at B, if you want to compute, so if you want to compute at B, so you can compute this further. So this pressure will extend from here, and it will go like this. So at 3 plus D, 3 meter plus this is the depth of embedment. So 3 plus D meter. This pressure, you can find it out. This will be equal to at 3 plus D, this if I call it as P3, so P3 will be P1 prime plus. Now this you can calculate as K gamma prime into 3 plus d. So if I simplify it, this becomes 12 plus 1 by 3 into 10.19 into 3 plus d. So friends, you have seen that at the bottommost point, the pressure P3 is calculated over here, which is 12 plus K, that is 1 by 3 into 10.19 into 3 plus D. So the value is known to you. The total value of P3 is going to be 12 plus so much, and that's the value over here. Now, in order to calculate the passive pressure at B, so at the bottommost point, PP will be equal to Kp into gamma prime into D. Now Kp is 3, gamma prime 10.19 into D. So this becomes 30.57 times D. So 30.57 times D is the passive pressure at B. Now, the total thrust, active thrust, will be the area of the uh, pressure distribution diagram, which can be divided into three parts. One is the triangular part up to 2 meter, and from 2 meter up to the bottommost point, it is going to be 12. So that is area number 2. So 1, 2, and for the triangular part, it is going to be 3. So PA should be calculated. The total active thrust will be area of P1 plus P2 plus P3. So area of 1 is P1, which will be equal to half into base is 12, into height is 2. So P1 becomes 12. So it becomes 12 plus P2. P2 is the area of the rectangular part. So it is going to be 12 into 3 plus D. So 12 into 3 plus D, that is the area. So it becomes 36 plus 12D, that is P2. Now, plus P3 is this triangular area. Now, the triangular area can be calculated here. So, we can calculate it as half into base is going to be 10.19 into 3 plus D by 3 into height is going to be 3 plus D. So into 3 plus D becomes 3 plus D whole square. So P1, P2, P3, finally you get it P1 12, P2 you are going to get as 36 plus 12D, this is P2, and if you simplify this becomes 10.19 divided by 6, into, so 1.69 into 3 plus d whole square. P1, P2, P3 is going to be the value of PA. Now this PA is going to act at the location. If you want to calculate, you can find out the location. So PA into, let's say, it is acting from the bottom at a distance y bar. So PA into y bar equal to P1 into y1 plus P2 y2 plus P3 y3. This will be this. Therefore, y bar equal to P1 y1 P2 y2 plus P3 y3 divided by PA. Now, P1 is already known to you as 12, and y1 from the bottommost point you can calculate it. So from B it will be 3 plus D plus it will be 3 plus D plus a 1/3 of 2 meter. So 2 by 3. This is y1 from B. So P1 is acting from B at this distance plus P2. P2 is going to be already P2 has been 36 plus 12D multiplied by y2. Y2 from here it is going to be 3 plus D by 2. So it will be 3 plus D by 2. So this will be y2. So this can be written, or this can be written in a simpler way as like this. Is P2 is 12 into 3 plus D. P2 is 12 into 3 plus D, that is the value of P2, which is acting at y2 from here, that is 3 plus D by 2. So 3 plus D by 2 means it will be a square divided by 2. So plus P3 y3. What is P3? P3 is already known to us, 10.19 or 1.69. This is the value of P3 here, 1.69 into 3 plus d whole square. And y3 will be the 3 plus d by 3. So from base, it will be into 3 plus d by 3, right? So y3 is also known to you, divided by PA, which is already calculated over here as 12 plus 12 into 3 plus d plus 1.69 into 3 plus d whole square. So this is the value of y bar. So y bar in terms of d, you are getting it, and you can simplify it further and calculate the value of y bar. So y bar is this one. So you get the value of y bar in terms of d. Now, if you take a moment about algebraic sum of moment of all the forces about B must be equal to 0. So already you know P1, so PA is already known to you, and Y bar is also known to you. So PA into Y bar is already known to us. So PA into Y bar is going to be the value of P1 PA. So it is going to be PA into Y bar will create a clockwise moment minus PP, we can calculate it. PP, the force, will be half into 30.57 D, half into base into height, that is d square. This is equal to PP, which will be acting at d by 3. So into d by 3 equal to 0. Now, because PA is already known to us, Y bar is already known to us, so all the things are well known to we people. Substitute the value of PAY bar. The PAY bar is given by P1Y1 plus P2Y2 plus P3Y3, and this is the value. So it is going to be 12 into 3 plus D plus 2 by 3 first term plus the second term the value of PA and value of Y bar. You can just multiply it. So take the value of PA, take the value of Y bar, substitute it over here, and simplify. Solving this equation, we get the value of depth of embedment D. So one equation you will be getting after substituting PA y bar, and which will be in terms of D, and minus PP into D by 3, that will be also in terms of D. So you will be getting one equation in terms of D, and that quadratic equation, if you the cubic equation, if you solve it, you will be getting the value of depth of embedment. So depth of embedment in meter, and therefore you can easily calculate D provided equal to 1.3 times the calculated value of D. And that becomes the solution of this problem. So by simplified approach, you get one equation. By taking the moment and pressure distribution diagram, easily you can calculate. So this problem can be uh, easily calculated. So it is simpler than your rigorous method in Cantilever, where you are going to have the pressure distribution, which is going to be quite exact. Whereas in simplified approach, you take the active pressure on the right hand side of the sheet pile, and on the left hand side, you take the passive pressure, and then by taking the moment about this bottom point, you can get an equation in terms of D, and solving that, you get the value of D and provide the D provided. So, friends, with this simplified approach, we have covered up both in theory and also one example. So, I hope this has gone well to all of you. In case of any question, you can post it on my channel. Thank you very much.